Okay, so Solomon Harris, Alex, Paul, then Ismail Taylor, Ilyas, Rodriguez, Nick, Will Hostetler, Margie, Gage Levine, and Nathan Light. Thanks, Margie, for subscribing me on YouTube yesterday.
Oh, yeah. Yeah, I want to be updated.
Thank you. Okay, so guys, if you know, yesterday we did just the introduction of system of linear differential equations, and today we are going to see how to solve the system of linear differential equations, right? So we did up to here. I told you how to get the solutions. Now it is just not one vector. It's a number of vectors are there in one matrix. Guys, that's what we discussed yesterday. And the general form is x dot equal to ax plus f. F is the non-homogeneous portion. Solution is capital X that contains the vector x1, x2 up to xn, all column vectors. And then after once we have a solution, then we went over the linear combination. Linear combinations of the solution of the system of equation is again a solution of the given system of equations. And then after once we have linear combination, then after we went over the linear dependent and independent of the solutions. If you write your linear combination with some constants C1, C2, and C up to Cn, and all your constants are 0 at a time, that is called the linearly dependent. And at least one of them is non-zero. In that case, it is called linearly dependent, right? So this was just the preliminary, or I would say the introduction for the higher order difference, yes, I would say system of linear differential equation. And now we are going to start the new article, that is the homogeneous linear system, article 8.2 from your book. We are going to first focus on article 8.2.1 and then 8.2.2. 8.2.1, that is based on roots are real and distinct, means lambda eigenvalues are real and distinct. Roots are real and same, that is article 8.2.2, and article 8.2.3, that is nothing but the roots are complex conjugate. So again, we are following the same thing, whatever we have been following in chapter 1 and chapter 4. So same thing is there, introduction portion, then solution, right? And based on different roots, I would say. So let's start like this. Look at here, guys. Let me just join my mouse here. Okay, and yeah, this one is here too. So homogeneous linear system of equation, dx by dt is equal to x plus 3y and dy by dt equal to x plus y. Right, guys? So let me first write my left-hand side d by dt and x and y like this. That is my x dot. My coefficient matrix I can get like this, a equal to 2, 3, 2, 1, and x and y like this. Yesterday I showed you how to get the product of two matrices. So if you take the product of these two matrices, you are going to get these two equations. Here your size of the matrix is 2 by 2. Here the size of the matrix is 2 by 1. Number of columns in the first matrix, that is equal to number of rows in the second matrix. That means this product is quite possible. So finally, I ended up with x dot equal to ax form, where A is my coefficient matrix. And I told you that you are then after working with only your matrix A. First of all, we are going to find the eigenvalues, because this eigenvalue this time for the system of equations will provide you the nature of the roots. Nature of the roots, I mean to say that it could be real and distinct or real and same or complex conjugate, blah, 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 etc. So determinant of A minus lambda I, this is the determinant. Please guys keep in mind this thing. I am not taking matrix now. It is the determinant. So determinant of A minus lambda I equal to 0. Lambda is the eigenvalue. Plug the value of A. This is my determinant. Inside this determinant, I have matrix A. Lambda as it is. I is the identity matrix. Because size of the matrix is 2 by 2, you have to have same size over here for the identity matrix. 2 by 2 and 2 by 2 over here, 1, 0, 0, 1, that's the identity matrix. Suppose you are working with 3 by 3 matrix, you will be getting here 1, 0, 0, 0, 1, 0, 0, 0, 1, like this, right? multiply this lambda with this matrix. Constant is to be multiplied with each element over here. So here it is lambda, here it is lambda. Subtract it. So 2 minus lambda, 3 minus 0, 2 minus 0, 1 minus lambda. So I'm getting this form. If you open this determinant, cross multiplication minus 6, you are getting the quadratic equation. This quadratic equation, if you solve, you will be getting lambda equal to -1 and 4. Once you have these two, -1 and 4, these two real numbers, means roots are real and distinct. Because roots are real and distinct, I want all you guys to keep your formula sheet open. If you don't have the hard copy, please keep so open your canvas and try to look at the formula sheet. Do you remember this thing? Yesterday I showed you the formula sheet. So I want all you guys to open your canvas and try to look at the formula sheet that is there in your practice test assignment in the file section. So please do it right now. I'll give you 2 minutes. Please do it right now.
Sir?
Yes.
I'm getting the practice test, but the equation sheet is not with the practice test.
Yeah, same here.
Equation sheet is not there with the practice test. Are you sure?
Yes, sir. It says practice test 4, and it has both pages of the practice test 4, but there's no equation sheet that comes with it. It's just the 2 pages of the practice test.
Sir, I'm getting the same thing.
Okay, yeah. Anyway, guys, no problem. I will post that today, okay? So right now, let me just go back and let you know about the equation sheet. This is the equation sheet. Look at over here. Please keep in mind this thing. Whenever roots are real and distinct, in my case right now it is -1 and 4, so roots are real and distinct. So I'm going to find my x1. X1 is a eigenvector I'm going to find my eigenvector, right? And then after I'm going to find my vectors x1, x2, x3 like this. So whenever roots are real and distinct, it is e to the power lambda 1t, e to the power lambda 2t like this, right? So it is c1 e to the power lambda 1t, c2 e to the power lambda 2t like this. For roots are real and distinct, it's almost same. Whenever roots are real and same, at that time we will be a little bit more careful. See, now one more thing, whenever roots are real and distinct, actually this portion, number 1 and number 2, first part, case 1, they are almost same. They are almost same. Only thing is you need to be very careful about your size of the matrix and the multiplicity. What we mean by the multiplicity? Your size of the matrix, that is always given by n by n, right? Because it's a square matrix, so n by n matrix. So here, in my case, it is n equal to 2 because it is 2 by 2 matrix. 2 equations are there with 2 unknowns. So 2 by 2 matrix, n equal to 2. M is the multiplicity. Multiplicity, that means I have my first root lambda equal to -1 and lambda equal to 4, that is my second root. So lambda equal to -1 and 4, that means none of my two roots, any one of these two roots are repeated. Any one of these two roots is not repeated. And that means my multiplicity, I have just -1 one time and 4 one time. That means both the numbers are different and I'm getting just one time. Means my multiplicity of m is just 1 because I'm getting one root one time. Suppose you are working with cubic equation, or I mean to say suppose 3 by 3 matrix, and suppose it may possible that you are getting 1, 1 and 4, something like that. That means in that case your multiplicity of 1 is 2 because it is repeated twice, right? Like this. In this case, in my case, my m multiplicity is just 1. Size of the matrix is 2. So m is strictly less than n. That means my root is same as whatever I described over here. But that won't be the case every time. It may possible, suppose sometimes, that your two equations and both those equations, if you find the lambda, you're going to get same number. So multiplicity is equal to the size of the matrix, number n. In that case, we have to go through this case 2, this long part. x1, x2, x3 like this. We will be taking care of this thing later on. Right now, let me go back to my solution. Go back to my solution for my problem. Here, -1 and 4. So again, look at over here. My lambda equal to -1 and 4. One of these I would like to denote by lambda 1. Second one is lambda 2. M equal to 1 because multiplicity, none of these is repeated. So multiplicity is just 1. Roots are real and distinct. And you have to mention this thing too, guys, that M is strictly less than N here. Okay. And I keep this one aside, and then after I can go for the eigenvector. You need to find the eigenvector corresponding eigenvector you are going to get corresponding to each eigenvalues. So you are going to get different eigenvectors corresponding to each eigenvalues. Eigenvectors, now I have to use the matrix. Look at here, A minus lambda I matrix form and capital K1 equal to null matrix. Null vector is my eigenvector. This K1 is eigenvector. I have my lambda. I am working with my lambda equal to -1 first, and then after I will be working with lambda equal to 4. If I take lambda equal to -1, just plug the values over here. A is already fixed, is given to you. You already decided 2, 3, 2, 1. Lambda equal to negative, negative, positive. I is identity matrix. Add this one. K1 is K1, K2 because two components are there. Sorry. So here 2 plus 1 is 3, 3, 2 and 2. Use your calculator, give the command RREF. If you give the command RREF for this particular matrix 3, 2 and 2, 2, right hand side 0. So you can go for just 2 by 2 matrix in your RREF. Try to pick up all my words, guys. You have just 2 by 2 matrix, right hand side is 0. So whenever I fix my matrix in my calculator, I have to first fix M equal to 2 and N equal to 2. So M by N equal to 2 by 2 square matrix. And then I can go for math and RREF command like this. So RREF for this one will provide me 1, 1 and 0, 0. Or you can say 1, 0 and 1, 0. This 1, 0. Now please try to look at over here, guys. Whenever I have identity form is like this, 1, 0, 0, 1 like this. Or I can say 1, 0, look at my cursor in a column form. 1, 0 and 0, 1 form. Whenever I have 1, 0, 0, 1, 1 form, that column, that is called the leading element. This 1, 0 corresponds to my K1 and this 1, 0 second part corresponds to K2. My K1 over here, that's the leading element. But K2 is not in the standard form. Standard form means the identity form. I mean to say that 0, 1 form. It is in the reverse form here, 1, 0 form. So my K1 is a leading element and K2 is a free element because that is not in the standard form. So I would say this one is my leading element. This one is my free element. This one is the free element, right? This one is the free element. If you solve this one now, 1 times K1 equal to 0 and 1 times K2 equal to 0. So K1 plus K2 equal to 0. That's what I'm getting. K1 plus K2 equal to 0. K1 plus K2 equal to 0. You are allowed to take only your free elements on your right side, not the leading element, please. So leading element, here 1, 0 form corresponds to K1. You have to keep that one on your left side. Free element on your right side. Free element means you are allowed to choose your different values of that K or K2, what it may be. K1, K2, what it may be. Suppose I choose, you can choose any value. Always try to choose some non-zero values. Sometimes 0 also depends, right? But don't go far from 0, 1 like this. 0, 1, half, 2, that's okay. Try to choose your K1 or K2, or it may be your free element in such a way that you should avoid your fraction part for K1 or vice versa. I repeat, your K2 in such a way that you are avoiding the fraction part over here. Most of the times it is possible, sometimes it is not possible. In that case, you can't do anything, just go for the fraction. But as far as possible, try to avoid your fraction for the simple calculations. My capital K1 stands for, that is the column vector K1, K2, K1, K2. I found my, suppose I choose K2 equal to 1, so my K1 equal to -1. So -1 and 1, that is my eigenvector. K1, -1 and 1, that is my eigenvector. And that's why my solution, my x1, that is equal to, just by that formula set, my x1 is equal to K1 e to the power lambda 1t. K1, I figured it out, eigenvector -1 and 1, actually constant, and e to the power lambda 1 was -1, so negative of t. That is my x1. So that's why I put the big box over here. I fixed my x1. Now, I have to repeat the same process for x2. I mean to say, I will start with lambda 2. Lambda 2, that is the another eigenvalue. Let me just repeat the same process. Replace this lambda, negative lambda by 4 or lambda by 4. So it is a minus 4i. A minus 4i. 4 is over here, right? If you do like this, a minus lambda equal to 4, a minus 4i. So 2 minus 4, so first is -2. 3 minus 0, it is 3. 2 minus 0, it is 2. And again, 1 minus 4, it is -3. So my matrix is different over here now. Again, give the command RREF, reduced row echelon form in your calculator TR 83, 84, 89, whatever you are using. Use that command over here. You will be getting like this 1/2 and -3/2. In your calculator, you will be getting -1.5. Again, I told you that if it is possible, try to write the fraction, avoid the decimals too. But anyway, so here it is. But you can see here 10 form. So standard form 1001. Here 10 form. First column is good to go. First column is my leading element. Excuse me. My leading element. And my second one is a free element because that is -3/2. It's not of 0, 1 type. It's not of 0, 1 type. So that's why this is my free element. K1, K2 and 0, 0. So 1 times K1 minus 3/2, K2 equal to 0. Solve this, just open this one, product of the matrix, and you're getting this one. K2 is your free, that means I can send that one to the right side. If you send this K to the right side, now look at over here. As I told you that try to choose your K2 in such a way that your K1 should not be in a fraction form. If I choose K2 equal to 2, 2 will get cancelled out and my K1 equal to 3. So as far as possible, try to avoid fractions for your K1, K2. So here K2 equal to 3 and 2. And my x2 solution from the formula set, my x2 equal to K2 e to the power lambda 2t. K2 is 3, 2. Lambda 2 is 4 and 2. No, sorry, 4 and t. One may say like this, that suppose I want to choose K2 equal to 4. Good, you can. Because 2 2s are 4 and -6. So K1 and K2, they are, small K1, K2, right? K1 depends on K2. Whatever choice, whatever you are choosing your K2, it depends on your K1. So it changes, don't worry about it. Okay, so that is x2. I put the second box over here. My general solution in the formula sheet says that now I have to multiply this and this both by some constants and sum up, add them. So C1x1 plus C2x2, that is my general solution. Don't forget to plug the value of x1 over here. So C1 -1 1 e to the power -t, C2 3 2 e to the power 4t. That is the solution of your system of equation. It's a general solution in the form of the matrix. But I told you yesterday, this X is not just one vector. X is a matrix, it's a column matrix. It contains your element or your vectors x1 and x2. So it will look like this one. Look at here. It will look like this one. My general solution C1x1 plus C2x2. If you want to stop over here, I don't mind. Here, I don't mind. Fine. I will assume that you understood the problem correctly. But the main solution would look, it will look like this. My X is nothing but xy. C1 as it is. My x1 was this one. x2 is this one. If I open this one, so negative of C1 into the power -t and 3C2 to the power 4t, that is my x and y equal to this one. So x and y, whatever I was looking for over here, starting in the beginning of the equation, my x and y, these unknowns, we are looking for these unknowns, and these x and y, they are the solutions. These solutions are given in this form. These solutions are given in this form. This is just simple two equations without any initial conditions. But suppose I provide you some initial conditions. In that case, you have to use those two initial conditions to fix your constants C1 and C2. So that's the easy task. But that is after reaching up to here, after you get this step, after you get this general solution. Then after you can apply your initial conditions and try to figure it out, the values of the constants. That's it. Sounds good? Right? Because here x is a function of t, y is a function of t. Suppose I give you that x at 0 equal to 1, suppose. Right? So x at 0, t equal to 0. So this is the left hand side is 1, left hand side is 1, e to the power 0 is 1, e to the power 0 is 1. So it is negative c1 plus 3c2. So 1 equal to negative c1 plus 3c2. Same here. Y at t, my second condition is y at 0 equal to, suppose 2. So here it is 2. E to the power 0 is 1. E to the power 0 is 1. So c1 plus 2c2 equal to 2. You have c1 plus 3c, negative c1 plus 3c2 equal to 1. c1 plus 2c2 equal to 2 over here. So all these two equations to get your c1 and c2. That's it. So initial conditions for the system of linear equations, they are very, very, very simple. Make sense? Any doubt in this example, guys? Any doubt in this example, guys?
It seems like the type of thing, sir, where you could have a lot of little mistakes that could add up over time.
Yep. Yeah. So please, first few examples, I think you need to be very careful because actually you are doing simple calculations, but make sure that if your first number is wrong, something is wrong in the first number, then the whole example will be wrong. So please make sure this thing, please. But it's not that hard. It's easy. Look at here. A minus lambda I equal to 0, determinant, and then the vector, whatever the eigenvalues we have. Use these different eigenvalues to get your different eigenvectors, K1 and K2, and that's it. This capital K1 boldface means it's a vector. Actually, it's a vector. Please keep in mind this thing. It's a boldface, is a vector. Any doubt? Shall I proceed further?
Yes, sir.
Second example, practice test example number 7. Practice test example number 7. Paul Mustaine, he requested me to post the solution of the practice test. Actually, you should not request me like this. You can't ask me for the solution, otherwise there is no purpose of homework. But even though I posted that solution day before yesterday night at almost at 11:20, and then after I removed it yesterday, right? I just kept that solution online in your canvas for a day, and then after I removed it. If you want to follow this one, of course, all these things are already there on YouTube. So please look at this one if you want to do this thing, right? Look at this one, try to get your solutions, but I don't want you to directly adopt your solution or adopt my solution. I first want you to work by your own, and that is the reason why I removed that solution from your canvas file. So please do this thing, guys. If you are not getting any of the things or some of the things from these videos, that's fine. We can discuss. We can discuss over here. We can discuss in our daily review session of 15 minutes. Dx by dt equal to x plus 2y, dy by dt equal to 4x plus 3y. Exactly same thing. D by dt is outside an x and y, or you can write x dot y dot. Coefficient matrix is 1, 2, 4, 3, and xy. X dot equal to x form. A minus ax equal to 0. Determinant. Plug the value of a. Lambda as it is. Lambda is like this. So cross multiplication here and then minus sign here equal to 0. So open this determinant. You are getting two values of lambda, negative 1 and 5. Size of the matrix is n. That is 2 by 2. So it is 2. None of the roots is repeating. That means multiplicity is 1. 1 is less than 2. So m is less than n. I forgot to write it down over here, but you have to mention this thing. M is less than n. Now, let me choose my first eigenvalue and try to fix my first eigenvector corresponding to the eigenvalue lambda equal to -1. So I'll plug lambda equal to -1, A is over here, 1, 2, 4, 3, and then after you're getting 2, 2, 4, 4. RREF will give you this form, 1, 0, 0, 1, 0 form. First one corresponds to K1, second column corresponds to K2. First one, there's a leading element. Second one is a free. So let me send this second, it's a K2 on right side. Choose your value of K2. You can choose -1, 1, whatever you want. So I'm getting my capital 1, K1. First eigenvector corresponds to eigenvalue lambda 1 equal to -1 in the form of -1 and 1. And then after, I can repeat the process for lambda equal to 5. So lambda 2 equal to 5 or lambda equal to 5. Again, this is the matrix RREF. RREF, you can see over here, first one is a leading element, second one is a free element. Send this K to the other side. Here I'm getting 1 by 2. So just to avoid the fraction, I would like to choose my K2 equal to 2. So 2 and 2 will get cancelled out. So I'm getting K1 equal to -1. K1 equal to, other side is positive. Yeah, so +1. So K2 equal to 1 and 2. That is my second eigenvector, right? I did not write over here, but I think I would recommend if you guys to write down here after K1, write down your X1. So X1 equal to K1 e to the power lambda 1t. So K1 e to the power lambda 1, that is my X1. X2 equal to K2 e to the power lambda 2t. So K2 and e to the power lambda 2t, right? So finally, my general solution is X equals C1 X1, C1 capital X1, C2 capital X2. Capital X1 is this one, capital X2 is this one, plug the values, and this is the solution. Or in general, you can write it down. Capital X is nothing but small x and y. Just write down these two equations. That is the solution of your linear two equations, couple linear equations. Sounds good? Any doubt, guys? It's exactly same as your previous example. Exactly same as the previous one. Shall we go for the next? Shall we go for the next, guys?
Yes, sir.
Okay. This is the homework problem. Just if it is possible, solve this problem by your own. It's simple. Okay. Another example is there. Question number 7, I think is the same one. I think so. I don't know. It is just another example. Same way. Question number 8, practice test. dx by dt plus dy by, that is equal to 3x plus 2y plus 4z. 3 equations, 3 unknowns, right? Again, you are getting square matrix. Make sure that you can use the system of linear equations for a square matrix. So your n here is, n here is 3 by 3 matrix. 3, 2, 4, 2, 0, 2, because it is C. So 2, no Y is there. So 2, 0, 2, 4, 2, 3, 4, 2, 3. 3 by 3 and equal to 3. A minus lambda I cubic equation. So 3 minus lambda, I just hide this row and this column, this row and this column. So whatever is left out, write down in terms of this one. Signs are alternating. So you start with plus sign, then minus, then plus, minus, then plus. So minus 2, and then hide this column and this row. So 2, 4, 2, 3 minus lambda is over here. Plus 4, hide this row and this column, the same row and this same column. This just hide this one, this cross-section part, this row and this column. So left out part is this one, the determinant, that is equal to 0. Open this determinant, you will be ended up, my gosh. You will be ended up with some cubic equation. Look at here. If you want, you can take the factors like this, otherwise it is not required. You can just open the brackets and you are ending up with some cubic equation. Lambda plus 1. Okay, here lambda plus 1 here, here and here. So lambda plus 1 is common, just take it out. Inside the bracket you have quadratic equation. Take the factor of this quadratic term. That means you are getting x lambda plus 1, lambda minus 8, lambda plus 1 equal to 0. Lambda plus 1 square means couple of my roots are repeated now. So lambda equal to -1 and 1. So 2 roots are repeated means my multiplicity is 2. Multiplicity is 2 and 1 is different. But still my size of the matrix is 3. So n is 3. So still m is less than n. So still I am working with my first part, solution of the first part. Because of these 3 eigenvalues, lambda 1, and 8, let me first let you know how can I, for same eigenvalues also we can get same different eigenvectors, guys. I would say that other way around, for repeated eigenvalues, eigenvectors are different. For repeated eigenvalues, eigenvectors are different. How? Look at here. A minus lambda I k1 equal to 0. If I take suppose lambda 1 equal to -1. So if I plug this my matrix A as it is minus lambda I, so minus lambda is equal to -1. So I'm going to get -5, like this is the matrix. Right inside 0. K1 is now small k1, k2, k3 because 3 unknowns are there, x, y, and z. RREF gives us like this 1, 0, 0, 0, 1, 0, -1, -half, and 0. First two, K1 and K2, they are in the standard form, leading elements. Third one is a free element. Only K3 is a free element. So keep your K1, K2 one side. Oh, I'm sorry, my bad. Where I was? Yeah, here, right? Yeah, so I'm good here. So this is my K1, this is K2. They are leading elements. K1 is only free element. So just send only K3 to other side, K3 to other side. And choose the value of K3. Look at over here, K1 plus K2, K1 minus K3 equal to 0. K2 minus K3 equal to 0. That means K2 and K3 are there, K1 and K3 are there. If you choose your K3 equal to suppose one number, suppose I take K3 equal to 2. Why K3 equal to 2? Because I want to avoid this fraction. If I choose this K3 equal to 2, this 2 and 2 will get cancelled out. So K1 equal to 2 and K2 equal to 1. So K1 equal to this one and X1 equal to 2, 1, 2. So X1 equal to capital K1 e to the power lambda 1. Lambda 1 is 8. So I started with 8. So lambda 1t. Right? Lambda 1t. This is the different root than this one. So that's why these are the repeated roots. This is the different one. That's why I solved first for lambda 1 equal to 8. And I got my eigenvector K1 equal to this one. And my first solution part is X1 equal to this one. Now I would like to go for this -1 and -1. If I take suppose lambda 2 equal to -1. So in that case, again, I am getting like this. This one and K2 is K1, K2, K3. Use again RREF. In this case, this time I'm going to get 1, 0, 0, half 0, 0, and 1, 0, 0. Means only K1 is leading. K2 and K3 both are free. Please, 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 guys. It is always, most likely it happens that whenever you have repeated eigenvalues at that time, you have at least you have two vectors, K1, K2, they are free. 2 are free and 1 is the leading one. So K1 equal to K2, K3 free, I would like to send to other side. That means I'm allowed to choose now for K2 and K3 simultaneously. Let me choose suppose K2 equal to 2 and K3 equal to -1. Right? K2 equal to 2 by 2 because 2 can cancel out and K3 equal to -1, or you can choose 1, or 0, whatever you want. So I'm getting my K2 equal to 0, 3 and -1. 0, 3 and -1. But that is for my lambda is equal to -1, first -1. I have another -1 is there as lambda. So that's why I want to change my assumptions, my choosing, whatever I chose, let me change these numbers. Now I would like to choose K2 equal to -2 and K3 equal to 1. Just let me change the sign. Yeah, I can do that thing. Let me just change the sign. And I'm getting K1 equal to here, 0 or what maybe. That means I'm getting here it is K2 and here is K3. Third eigenvector, 0, -1 and 1. Please keep in mind this thing that number of eigenvalues must be equal to number of eigenvectors. For repeated eigenvalues, you are getting separate different eigenvectors. Size of the matrix must be equal to number of eigenvectors. Please keep in mind this thing. Okay, so K3 is equal to this one. Now my x2 is nothing but K2 e to the power lambda 2, 3 and x3 equal to K3 e to the power lambda 2, 3. You fix your K2 and K3 choosing different values of this small K2, K3. So these are the values. But again, my m is less than n, and that's the reason we'll hear my m is less than n, and that's the reason I'm following my first part of the formula set, C1, X1, C2, X2, C3, X3, plug the values, and that is the answer. If you want to write it down, small x equal to 2C1 e to the power separately, all this, that's fine. Otherwise, I will accept this one. But that is the answer. So that is K1, K2, K3, 3 roots are there. Any doubt in this example? Just try to refer the same one. Let me go back to the beginning of the example. Just refer this one. I give you a couple minutes, and then after we can go for the next article. Okay, guys. Done? Sounds good. Now look at here, guys. Repeated eigenvalues m equal to n. In this example, you have m equal to n. You are given directly the coefficient matrix That means that corresponds to two differential equations because it is 2 by 2. So simultaneous linear equations, two differential equations are there. So sometimes I may provide you differential equations, sometimes directly I can provide you the coefficient matrix like this. It is 3, -18, 2 and -9 and x. 2 by 2 means n equal to 2. A minus lambda I, 3 minus lambda my -18, 2 and 9, -9 minus lambda equal to 0. If you open this determinant, you are going to get lambda plus 3 square equal to 0. So lambda equal to -3 and -3 because of this square. So size of the matrix is 2. So n equal to 2. Two roots are there. Both are repeated. Means multiplicity is m. That is 2. So m equal to 2, n equal to 2, m equal to n. N equal to n, that means now you cannot use your first method from the formula sheet. You have to go through case 2. Part 1 is same as your case 1. So lambda equal to -3, a minus lambda I k. Lambda equal to -3, so a is this one. So 3 plus 3 is 6, -18, 2 and -9 plus 3 is -6 and k1, k2. RREF gives you 1, 0 and -30. K1 is a leading element. -3, 0 is, this one is not leading free element. Let me send it to the other side. Let me send this one to the other side. So K1 equal to 3, K2. If I choose suppose K2 equal to 1, I'm getting K equal to, or K1, sorry, K equal to 3 and 2. You can write K1, what do you want? 3 and 2, 3 and 1. So my X1 equal to K e to the power lambda 1t, K1 equal to 3 and 1, 3 and 1 e to the power -3t. Up to here, it is exactly same as your previous example. Now, because my multiplicity is same as my order of the matrix, we have to consider a minus lambda I p equal to k. Whatever k I am getting over here, I'm using this k over here to fix my another eigenvector. I'm using my previous eigenvector to fix the next eigenvector. And that's why you could write here K1 and K2 here, that's fine. But just to make sure, I wrote it down over here, capital K, and here it is P. So you can come to know this thing that this is completely different eigenvector we are looking for based on, depends on your previous eigenvector. So let me write now again lambda equal to -3. So we don't have any choice. A plus lambda I, P is P1, P2, K is K1, K2, that is 3 and 1. We have 3 and 1. Plug this value of your matrix and you are going to get 6, -18, same thing. P1, P2 and this one. But now your size is not just 2 by 2. Its right hand side is not 0 now. It's not 0 like the previous one. It is now non-zero. So 3 and 1. So I have one row, second row, first column, second column, and third column. Whenever I'm going to fix my RREF, before that, whenever I fix my matrix, at that time I have to fix 2 rows and 3 columns. One column, second column, and third column. 3 columns. So your size of the matrix in your calculator would be 2 by 3. 2 rows, 3 columns. 2 rows, 3 columns, like this. And that is your P1, P2. So P1, P2 is 6. I put the dotted line. Please use this dotted line because right hand side will provide you the solution. So please use the dotted line. Okay. And then give RREF. If you give RREF over here, you're going to get 1, 0, -3, 0, and 1 by 2, 0. So 1, 0, that is the leading element. -3, 0 is non-leading free element. And 1 by 2, just constant right hand side. Let me send to other side. I can send this both to other sides. So I'm going to get P1 equal to -3 P2 plus half. So I'll send P2 is free, right side. So 3 P2 plus half. If I choose P2 equal to 0, you can choose anything. You can choose 1, but in that case, you're going to get fraction. See, now this time you can't avoid fraction. You can do like this, P2 equal to half, then P1 equal to 3 by 2 plus 1 by 2 is 2. But again, now P2 is half. So any one of these will be a fraction. So you can't do anything this time. So just take P2 equal to 0 or 1, whatever you want. So let me choose P2 equal to 0. So my P1 equal to 1 by 2. So my P is P1, P2, 1 by 2 and 0. I'm sorry, 1 by 2 and 0. That means I'm going to get X2 equal to now. This is important. Once you get your vector P, then stop it. Look at here, how I used my solution. X2 equal to 3 and 2. Whatever solution, look at my cursor, whatever solution I got it previously with my first lambda 1 equal to -3. So 3, 1 e to the power -3t. I already received the solution. Use the same solution and multiply that by one polynomial t. Actually, we are multiplying by t to the power 1 by 1 factorial. This is 2 by 2. If you are working with 3 by 3 matrix, in that case, what will happen? What will happen that you are multiplying your first solution by 3, 1, t square by 2 factorial. Now, as far as concern of t to the power 1 and 1 factorial is 1. Doesn't make any difference. But if you have 3 by 3 matrix in that case, and all 3 roots are repeated, will here please say that guy to go outside, please. This is very important thing, please. So 3 and 1, whatever you have over here, 3 and 1 e to the power negative 3t, multiply that one by t square by 2 factorial. So always your polynomial in terms of t, if it is 2 by 2, you have to multiply your first root by just t, and then after you can write t to the power 0 by 0 factorial. But t to the power 0 is just 1, 0 factorial is just 1. That's why we didn't write anything over here. Look at my cursor. But actually we are writing our solution in the descending order of my polynomial t. If it is 3 by 3, you have to start with t square by 2 factorial. Then for second root, means the second root, first root is like this, t square by 3 factorial, first root. Second one is t to the power 1 by 1 factorial, second root. And third root is whatever you are getting over here as p, third root, if it is 3 by 3 matrix. So I just explained to you in a very simple way without using the formula. If you look at the formula now, you will realize this thing, how I have used this form, this x2. General solution is quite simple. General solution is x equal to c1 x1 plus c2 x2. Just plug your x1 and x2, whatever you figure it out. Only thing is how you fix your x2, that is more important or second part I would say, that is more important, that is different, because here we are using our previous solution, previous eigenvector, k1 is the right hand side, RREF everything, and then after polynomial form, 2 by 2 matrix means we are starting with 1 less power to the power 1 by 1 factor. If you have 3 by 3 matrix, you are starting with t square by 2 factorial and so on. So please keep in mind this thing, please. Does it make sense? Now, this is the solution, the general solution. You can write it down separately too. Now let me go back to the formula sheet. Let me go back to the formula sheet. You can see over here, case 1 is fine, case 2, whenever m equal to n. Whenever m is equal to n, in that case, what will happen? M equal to n. In that case, x1 equal to k11 e to the power lambda t. That is same as whatever we figured it out. But x2, look at here. My first root, k11, I am adopting the same root over here. Same root here with my polynomial t to the power 1 divided by 1 factorial. And k2, whatever I am getting my p, that is my second root, k22. My x1 was not multiplied by anything first time. Same way my second part p vector is not multiplied by anything. Whenever you have diagonal element k11, k22, k33, they are not multiplied by anything. Look at here. And all your previous terms are multiplied by t to the power 1, t square to the power 2 factorial like this. Are you getting me? Here I have just 2 by 2, so I just used first one and second one, t to the power 1 by 1 factorial. But if you go for t3, you have to use this one, this part. Same way, m solutions, this one. I'm not going to ask you more than 3, maybe 2, just 2, right? 3 by 3, again, it will be a lots of work for simultaneous linear equations. So most likely I'm going to ask you 2 by 2 matrix whenever repeated roots are concerned. Whenever m equal to n is concerned. I'm not telling you about m is less than n. For m is less than n, I may ask you 3 by 3, but for m equal to n, I would like to restrict to 2 by 2. Right? I don't want to create any confusion or complications for you guys. I just want you to know the material thoroughly, to understand the concept. That's what my intention. I don't want to put you in trouble. Any doubt, guys? Any doubt in this solution? Oh, sorry. Yes. Yes. Any doubt in this solution? Yes or no?
No.
I can give you a couple of minutes. Try to look at this solution, please, guys. Mainly the second part. Last one. Roots are complex conjugate. Whenever complex conjugate roots are there for system of linear equations, it's very simple. It's very simple. How? Look at here, I'll let you know. You would like it. Dx by dt equal to 6x minus y, dy by dt equal to 5x plus 3y. Example number 9 from the practice test. This example is very similar to that one. 6, -1, 5, and 4. See, I wrote it down everything for you. If you are missing something, just try to look at this one and then work accordingly. You won't face any problem solving your homework problems. A equal to 6, -1, and 5, and 4. Characteristics equation or eigen equation or proper equation, whatever you want to say, determinant of A minus lambda equal to 0, solve for lambda, quadratic equation, 5 plus or minus 2i, roots are complex conjugate of each other. Let me work with any one of these two roots. Let me work with 5 plus 2i, 5 plus 2i, and try to find my eigenvector corresponds to this 5 plus 2i. So if I do this thing, I'm going to get like this, 6 minus 5 minus 2i minus 1 and this one. Now, look at here. Because of this I don't think that you can use your calculator. Your calculator that is for the real numbers, not for the complex numbers. So RREF probably it would be a little bit harder for you. But if you look at over here, I have some number over here in terms of I, which is not 1. I know this thing. That means I can assume something like this. It looks that my first vector K1, that is not the leading element. That's not the leading one. But my K2, if I take this negative out, I'm getting 1 and here it is some number. So 1, 0, and I can make this one 0, right? By applying some elementary row transformations, I can make this one 0. That means this is, or other way around too. That means this is my leading element and this is my free element. But suppose someone says that why not this K1 is free element and not K2? Yes, you can do that thing too. Both the ways you can do these things, this example. Here it is 1 minus 2i and 5, right? If I divide throughout by 1 minus 2i, what I'm going to get? Here I'm going to get 1. Here I'm going to get 1 over 1 minus 2i, right? 1 over 1 minus 2i, something like that. So in that case, this is not 1, 0 form, but this will be 1, 0 form. Because you can divide by this one, here it is 1, and you can make this one 0 by elementary row transformation. So your K1, either K1 is your leading or K2 is your leading. I just want to stay with the same theme, whatever I have been doing. So let me keep this 1 minus 2i. This is my leading one, this is my free one. So 1 minus 2i, K1 minus K2 equal to 0, K2 equal to this one, K2 equal to this one, right? K2 is free. Am I right, guys? Or here, no, I'm sorry. Here I have my K1 is free, as I told you. I'm sorry. I just work with K1 equal to free. K2 is my leading one because negative 1 is there. I'm sorry. So negative 1 is there. K1 is free. So K2 equal to 1 minus 2i times K1. 1 minus 2i times K1. If I choose, suppose K1 equal to 1, my K2 equal to 1 minus 2i. So K equal to K1, K2, 1 and 1 minus 2i. Right? Now my second eigenvector was just, here it is 5 plus 2i and here 5 minus 2i. Just I is replaced by negative I. Look at here. I is replaced by negative I. Exactly do the same thing over here, guys. Don't repeat everything. lambda equal to 5 minus 2i. So K2, directly I wrote it down. Whatever K1, I got it over here, 1 and 1 minus 2i. I replace this I by negative I. I by negative I. So it is 1 and 1 plus 2i. I am done. I told you. So complex conjugate roots for 2 by 2 matrix is quite simpler than the real numbers, real roots. See here, just I replaced by 1 minus 2i. My I is replaced by negative I. So 1 and 1 plus 2i. So K2 e to the power lambda 2t, 1, 1 plus 2i, and this one, right? That is my x2. That is my x2. Now, if somebody says that, what's about the nature of these two roots, whether they are linearly dependent or independent? Go for Vronsky. Yes, your real root phenomena, Vronsky, will work over here too. So Vronsky of K1, K2, K1 is this one, my eigenvector, 1 and 1 minus 2i, 1 and 1 plus 2i. Open the determinant, 4i different from 0, 2 eigenvectors. See, we talked about the roots so far, whether two roots are linearly dependent or independent. Two solutions are linearly dependent. Here, two eigenvectors are linearly dependent or independent. Yes, two eigenvectors in this case for this particular example, because my Vronsky is non-zero, that's why they are linearly independent. My Vronsky is non-zero, and that's why it is linearly independent. So x equals c1, x1, c2, x2. Plug the values of x and x1 and x2 over here. X1 was my, but finally you have to separate your real and imaginary parts, because you are writing the complex form. One is x and then I times y. You have to have that solution. Don't just plug the values and leave it. No, don't stop over there. You need to plug the values and you need to separate your values in terms of real and imaginary parts. So x1 and x2, if I plug the values of x1 and x2, x1 is this one, 1 and 1 minus 2i, e to the power this one. E to the power this one, I mean to say that e to the power 5t times e to the power 2it. But e to the power 2it means e to the power I times theta. That means cosine theta plus I sine theta. Euler's identity. Look at here. 2ti. E to the power theta I or I theta. So cosine 2t plus I sine 2t. Cosine 2t plus I sine 2t. Let me separate my real and imaginary parts like this. See, I just leave it to you. So C1 times cosine 2t plus C2 times cosine 2t, right? And C1 1 minus I times this one, and 1 minus 2i C2 times this one, e to the power 5t out. Excuse me. Allergy. Anyway, guys, so that's how you can get the solution for the complex eigenvalues, complex conjugate roots for the system of two equations. One more example for cubic equation, n equal to 3. My roots are, I have done the complete example over here. My roots are -1, and 5. So multiplicity is just 2. So again, m is less than n, means case 1, right? So, and this is, I think, one of the examples from your practice test again, if I'm not wrong. Yes, practice test example 10C. Everything is done. Only thing is you need to just work hard. Look at here, guys. Look at here. Look at here. I go really very slow because when you refer the video at that time, you will realize the whole picture, whole page, whole solution. Cubic equation is there. That's why I just go for trial and error method. Lambda equal to -1 is one of the roots, because lambda equal to -1 satisfies this equation. -1 cube is -1, -3, -1, -3, -4, -5 is -9, and positive 9 is 0. So lambda equal to negative means lambda plus 1 equal to 0 is one of the roots. So divide this one by lambda plus 1 and you are getting some quadratic form. Look at here. You are getting the quadratic form. So this multiplied by this, that is equal to 0. Your remainder and this one, that is equal to 0. Lambda plus 1, quadratic form. So lambda equal to this one. That's how you can find the eigenvalues. And then for different eigenvalues, you can find the different eigenvectors. And that's what I did over here using RREF. Look at here. Everything is well defined. Everything is done. One more example. I think this is the same example which I did based on complex eigenvectors, eigenvalues. And that is the end of this chapter. One more example. I think that's just a repetition. just the repetition. That is the end of this chapter, guys. What you want me to do? You want me to continue with the new chapter, or you want me to stop over here? Just decide. I give you 1 minute. I'll be back.
What do you guys think?
To stop.
I don't care. Doesn't matter to me.
It's 10:55. We'd be getting out an hour early if we stop, which is sleep time.
Wait, when's our test? Tuesday or Monday?
Wednesday.
Wednesday next week, I think.
Oh, we have a while there.
Wait,
Yeah, we got like 3 sections.
wait, our
do.
4th test is Wednesday, and then when's our final then? Friday?
Friday.
Yep.
Next Friday.
Wait, but Thursday's a reading day, right?
I think so.
So
Yeah.
I think next Thursday is a reading day.
Yes, guys. What do you prefer? You want me to start the new chapter? You have enough time. Don't worry. Or if you want to get stop over here, then we start the new chapter tomorrow. Yes.
Sure. I'm
What?
all about stopping.
Yeah, I'm good with stopping.
Yes, girls.
Yeah,
That's
that's
fine.
Okay, guys. So that's all about your chapter 8. Working on all the problems. This time I'm not going to provide you any extra time for your homework submission. You can submit your homework and your exam simultaneously on the test day. So please make sure, guys. Please make sure. And next thing is when you want your exam. You want your exam on Friday? Today is just Wednesday. We can finish the syllabus tomorrow if you want. And you can take your exam on Friday. If you want, you can take your exam on Monday or Tuesday. Choice is yours.
I'll do Monday.
I'd say
Monday.
Tuesday.
yeah, I'd rather do Tuesday.
Tuesday's
Yeah.
fine.
Tuesday for me too.
Yeah, I
Tuesday's good,
can't
sir.
do Monday.
4 Tuesday, 2 Mondays. Other guys?
Yeah, I think Tuesday's better, sir.
Thank you.
Bye.
Bye. Take care.
Have a good one.
You too.